So good morning, everyone. My name is Mohammad Nobi. I am from University of Texas at San Antonio. I am working under supervision of Dr. Krishnan and Dr. Sandhu. So today I'm going to present our paper toward deep learning based access control. So as we know that there are many access control approaches.
I'm sorry, here at the online presentation, we can see your presentation slides and not the directly presentation. So you maybe shared the wrong screen.
So you want me to share the screen?
You shared your screen where we can see your PowerPoint application.
PowerPoint. I can start slideshow.
Yes, now it's fine.
It's good now?
Yes, thank you.
Okay. So there are many machine learning, there are many access control approaches that includes the ECHOs, RBAC, ABAC, and there are numerous advancements over time. And however, there is still one issue still remain the same, which is human administrator needs to maintain and manage all those accesses. So that brings all the inefficiencies and errors that could include over provision and under provision. So if we think about a system, for example, the system has their access control state in the form of authorization tuple, which is a triple of user, resource, and set of operations. And the system has a set of user metadata, which is unengineered version of the information, as is user information and resources information. And if we want to transform it to a modern access control system, the first phase would be probably to engineer the attributes, which is based on the available metadata of the user and metadata of the resource. Will extract and design access control attributes. For example, in this case, we consider combine both join date and credit score to get a credit status, C status attribute. And the next step is to assign their attribute values. And the phase two, it would be based on those engineered attributes and the existing access control state will mine the policy. So, for example, we designed a rule that is based on that where we covered a couple of tuples from the access control state, and eventually we'll mine other rules to cover all those given access control state. And based on the this mine policy, whenever a request comes into the system makes the access control decision based on available engineered attributes and the mined policy. So in this example, we see that there are multiple phases where a human administrator is involved, and also we mostly focused on the given access control state and what if a scenario that where we have a user resource having a different combination of their attributes, and how efficient the model is making in their access control decision. So that is the actually generalization problem in access control. And we say that a model or an access control system is more generalized that can make better access control decision from the user for the user and resources, those they didn't see during mining process. So we wanted to see the current advancements of deep learning. And it seems like the deep learning is successful in many areas. And they could learn from examples, and they learn directly from the raw information without feature extraction. And they could obtain an excellent accuracy. So what if we apply deep learning in access control? Could it learn from existing access control state? And could it learn directly from the raw metadata? And also, could it make access control decisions that are more accurate and generalized? And eventually, for access control decision making, instead of making decision based on the rules and attributes, probably a neural network could replace it for access control decision making. And that will obviate other steps of, for example, attribute engineering and assignments, and also the policy engineering. So in this paper, we explored the advancement of deep learning, and we propose a deep learning based access control. We call it DLBAC. And here we contrast between the existing access control states models and DLBAC. As we see that DLBAC is trained based on, for example, for the simplicity, we assume that our access control state is given in the form of authorization tuple. And we see that a DLBAC, we can train a DLBAC neural network, and that after the training, we'll get a trained neural network that could eventually make the access control decision. So for the training, we didn't do any, we do not need to do any other engineering or feature extraction. We could directly train the model. And the DLBAC trained neural network model can make access control decision, as opposed to rules in the case of ABAC, and user assignments and permission assignment in the case of RBAC. So to evaluate how DLBAC can do that in practice, we implement a candidate DLBAC model. We call it as DLBAC alpha. And we, as a candidate deep neural network, we use ResNet. And also for the authorization tuple, if we have a system, we have a authorization tuple, and also the metadata of the user and resources. And for example, in this system, we have 4 operations. Then we can, in this DLBAC alpha, we actually convert all those for each user and resources. We make a vector of their metadata for the respective user and the vector of the resource. And we keep the flag for each of the operations they have access to. So this is the authorization tuple in DLBAC alpha. And we call a dataset, which is the collection of such authorization tuples. And we will use the term samples or authorization tuples interchangeably. So as you know, in access control, there is a lack of dataset, and therefore researchers generally rely on synthetic datasets. So here in this experiment, we essentially experiment both on real world and synthetic datasets. So first we'll talk about how we generate our synthetic dataset. So we generate a synthetic dataset using Xu et al. Method. And based on generated data, we visualize this using a t-SNE plot. So here in this plot, each dot represents an authorization tuple. So each color in the plot that represent the combination of the operations they have access to. So for example, for this given one authorization tuple is a 1 dot. So the color would be essentially the unique combination based on the OP1 and OP3. And the position of each dot that depends on the value of the metadata of both user and resources. And 2 tuples, they are close to each other. That indicates that they have very similar metadata values. And multiple tuples from the same color, that indicates that they have exactly same access combination. Maybe they are different user and different resources with different metadata values, but they have exactly same operations combination. So as we see that there are some groups, so they actually are grouped together. There are a couple of samples. They are grouped together, even though they have very similar metadata values, but they are grouped together with the same color. That indicates that they have exactly same access. So we could use a typical method to cluster them and make solve the access control mining problem. However, in real world scenario, it is not that easy. So we'll see there are much more overlapping among the samples. That indicates that having very close metadata values, they might have completely different access. So this is one example from one of the simpler real world Amazon dataset. And we see that there are much more overlapping. So to that extent, we try to simulate real world scenario as close as possible, and we generate a set of synthetic data sets. We generate 8 synthetic data sets with different number of users and resources and different level of complexities that we introduced in the data set. And we also experiment with 2 other real world data sets. So to prepare the training data for DLBAC alpha, we first convert the metadata value of the user and metadata value of the resources to a binary matrix. We encode them into a binary matrix representation. And here a binary matrix that actually represents a combination of user metadata and a resource metadata. So, and our aim is to train a neural network that will predict corresponding access probabilities for specific permissions. So as far as decision making is concerned, we take the user metadata, we take the resource metadata, we again encode them to get the binary matrix, and then we give it to the neural network that actually give us the probabilities for specific operations in between 0 and 1. So based on some thresholding, we do decide whether it should be denied or it is permitted. So to evaluate the performance of DLBAC, we create multiple instances of DLBAC alpha with other deep neural networks that includes DenseNet and ExceptionNet. To compare how well a DLBAC could do, we compare with classical machine learning approaches that includes support vector machine, random forest, and also MLP. And we also compare with some state-of-the-art policy mining approaches. And we evaluate the performance in different metrics that includes F1 score and TPR. So also evaluate the false positive rate. So a higher TPR indicates that a model is efficient in granting accesses. A lower false positive rate that indicates that the model or a policy that is efficient in denying access. In other words, we can quantitatively measure the performance of over provision and under provision. For example, having a lower TPR of a model, we could say that this is under provision. In other words, for false positive rate, having a higher false positive rate is the indication that the model is over provisioned. So we compared the performance with machine learning algorithms, and we see that the performance of DLBAC alpha instances are pretty consistent across data sets, and which is way better than the traditional classical machine learning approaches. However, we see that in the case of random forest, their performance is a little close to the DLBAC alpha for some data sets. But this difference is statistically significant. So we also compare with policy mining algorithms, and we see that DLBAC alpha instances performance is way better than the policy mining algorithms. However, in one method, their performance is closer, but that EPDML is a machine learning based approach. Essentially, they train a random forest to make the access control decision. So we also compare how efficient the DLBAC alpha in handling desired accesses and unwanted accesses. As we see that in the right figure, that classical policy mining approaches, so they could handle the unwanted accesses pretty well, and DLBAC alpha instances of performance is also closer. However, if we see the left figure, they're not, the policy mining algorithms are not as efficient as DLBAC alpha in granting accesses. So we could summarize here that DLBAC alpha instances can balance both over provision and under provision. Well, so at this stage, we understand that DLBAC alpha, they could do better access control decision. Now, if there is a request in the system and DLBAC alpha denied the request, so if we want to learn that why this access decision has been made by DLBAC alpha, we do not have any answer, because underlying model in DLBAC alpha is a neural network, which is a black box. Or even if we want to ask the question that what are the metadata that are influential in denying this access, we do not have that answer too. So we propose two approaches to understand the decision of DLBAC alpha, and we formalize this problem as a neural network interpretation problem. And based on that, our first method, integrated gradients method, that if we want to learn underlying intuition of a specific access request, we'll give all those information. We'll give the user metadata, we'll give the resource metadata and corresponding decision to the integrated gradients. Then integrated gradients will give us an attribution score across metadata of the user and resource. So the lower attribution score indicates that it is less relevant or it has less influence in this specific decision. So as we see that for this specific decision, there are two metadata, those are highly influential, and also there are other metadata that doesn't have essentially no influence at all. So and understanding a specific access request, it is also known as local interpretation. And we could also learn this kind of intuition across the requests for a specific operation, and that is also known as global interpretation. So we can apply this integrated gradients-based understanding in other aspects of the access control. So for example, there is a situation where a user, Carol, requested an access for a project C resource. However, his access has been denied. System administrators somehow know that there is another user, which is Dave. Dave has access to project C resource. System administrator could exploit the integrated gradients-based understanding to learn what are the important or influential metadata of Dave in having this access, and could replace the respective metadata of the Carol to get a modified version of the Carol's metadata. And if he could give all those information to the system now accepts the decision. So that indicates that that it strengthens the effect of influential metadata. And also this kind of interpretation can be utilized in user access modification. However, this interpretation technique, it doesn't establish the relationship among the metadata. So we also apply knowledge transferring technique to approximately understand the decision in the form of typical rules. So we get all the for a system, we get their corresponding access probabilities. For example, for a request, as we said, that instead of giving a permit or deny access, it gives us a probability. So we get all this probability, and we call these probabilities the knowledge of corresponding model for this specific system. And we can train a decision tree based on the probabilities that we get from the DLBAC alpha network. And this decision tree is the representation of the respective DLBAC alpha neural network. And we can extract a rule. That rule represents a local interpretation, and the tree as a whole represents as the global interpretation. So we list out a set of future research directions. So one issue is DLBAC alpha, DLBAC in the long run, there might have modification in the accesses in the system. So we have to see that how we can accommodate those changes if we need to make corresponding access decisions or any access control state modification in the system. So that is the administration problem of DLBAC. And also, as DLBAC is, we don't anticipate that it will readily replace the existing access control systems because there are issues that needs to be resolved. But DLBAC has the potential to run in tandem with other access control systems side by side, probably could help in different aspects. And also, as DLBAC is a neural network based system, like as other machine learning based application, DLBAC also has the problem with adversarial attacks. However, those are from access control perspective. Maybe there are some constraints from access control. There are some advantages and disadvantages that needs to be explored. And also, DLBAC is trained based on raw metadata information from the system. Those metadata could come from different areas of the system, different parts of the organization. So there might have some biasness, some fairness issues. So that needs to be addressed as well. So that concludes my talk here, and we uploaded all our DLBAC source code and datasets in GitHub. And thank you for listening, and I'll be happy to answer any question.
So questions?
Thank you for the presentation. I have a couple questions. One is, what size tools were you looking at for the user attributes and the resource attributes? And also, had you looked at cross dependency between sort of user attributes or resource attributes?
So first question is what size?
The first question is yes.
How many? So how many authorization tuples, or how many samples, or the number of attributes?
The length of number.
Okay, so for our experiments, essentially we considered 8 to 13 attributes. We explored it in different combinations. And what is the next question, please?
Did your research look at possible dependencies between user attributes or groups of resource attributes that certain resource attributes might occupy for together or might not occur together?
So that's the one thing actually we visualized here with so as you see in our visual dataset visualization. So there we showed that if they have so we said that if they have there is no notion of attributes. First of all, we do not have any notion of attributes. So we are working with DLBAC trained based on raw metadata information. So, but yes, might have some metadata. Those could be attributes comparable to the attributes in practice. For example, a designation. So, thing is, we visualized the data set and show that having a similar metadata value, they might have different access. And with we wanted how efficient a system is to capture all those relationships. So that's what we wanted to explore.
Thank you so much for the presentation. I have a question. So, I understand you are replacing the deterministic system, deterministic system. So, because in other version, the decisions are made on deterministic way. You also mentioned in your slide about over provision or under provision. So, how do you handle this situation? Because if you make a right decision, you're granting somebody access that you shouldn't do that. So I think that's
yeah. So that's a good question actually. So that's the thing we wanted to evaluate. That is it possible? Do DLBAC has the potential to do that? And as you see from our evaluation, so as you are saying that deterministic approach, they could better handle the accesses. Probably they are better at denying access. And we showed that DLBAC also has the exactly same, or not, if not exactly, very similar capacity. But in the case of granting accesses, they do not have that capacity because they are denying by default. So that's why we see that the system has a very lower TPR, which means that they are underprivileged. So keeping a system underprivileged is easier, that I will deny all the access, right? It is safe because we could deny it. However, we showed that if we need to really grant the access in practice, there might have some dynamic system, then complicated, complex system, you cannot just always deny. So in that case, how efficient DLBAC is in granting access. And we showed that it has way better potential than the traditional approaches.
Just one comment, actually, I believe that denying access is safer, but in the medical community, there's a debt actually because someone did not get access. And so they are very, very about access control actually.
Yeah, right. Thank you. Yeah.
So just one question related to, I think, implementation. So I saw that you were using some kind of image-based model specs, ResNet, for this, but it seems like your data is like just some kind of vectors. Right?
Yeah.
So how did you apply image-based model?
Yeah.
To this kind of data?
Right. That's a good question. I think this figure will give you the answer, because you see that first we have the metadata, user metadata, we have the resource metadata. So the first we encode them using one-hot encoding to get a two-dimensional binary matrix. So essentially, this binary matrix is representing an image. So you can say, in other words, that we are converting the metadata of the user and resources to a intermediate image, and that we train the ResNet on those images. So essentially, these two, one image, it represents the metadata of a user and a resource pair. For each of the pair in the system, we create a separate image.
Thank you. One last question from
Thank you for your presentation. So I'm especially interested in your synthetic data. So how did you generate them? Did you also use the machine learning model? And how did you evaluate them? How did you determine is this good data or hard data? And how close are they to real world data?
Yeah, it's a very good question. Actually, so let me give you. So we used the Shu et al. Method. So let me give you the reference. As you see the reference of this, so we used their method. It is non-machine learning based approach. So this is a data set for ABAC system. And how good the data set are, we compared with the data characteristics of the real world data set. You see that in real world, the data characteristics, there are much more overlapping among the samples. And we tried to simulate that characteristics, and we visualize in our system that there are a lot of overlappings among the samples, meaning that they are much more complicated. So we wanted to simulate the real world scenario as good as possible.
Any questions from the online participants? Okay, so I think we can thank the speaker for the wonderful talk.
Thank you.